Okay, so in this next video right here, we're going to consider fan out. Fan out is when a single transmission line divides into two. And the first type, which is the more common type, is called a parallel fan out. Now, a parallel fan out is very common on circuit boards or integrated circuits. It also happens in the power grid where you can have one feed line divide into two. And so we have to be ready to treat this. But here's kind of a diagram of how a circuit board might look with different traces on it, right? The gold color or copper or metal traces that are basically wires. So here is a transmission line right here that is running along, and it encounters this little circle right here. This circle is called a via. It's basically a tunnel through the circuit board that probably connects to another trace that you can't see this on the opposite side. So I'm going to draw this even though we can't see it. There may well be a trace that runs from the other side of that via and, for example, goes that way. Whereas on this side of the circuit board, it continues on toward some other target. Okay, so this is an example of a parallel fan out. One transmission line is coming in, it reaches a junction, and it divides into two transmission lines. If you've ever used a T-junction connector on a BNC cable, that's also a way to have a parallel fan out. The outer conductors of all three of these terminals are connected, and the inner conductors of all three are connected as well. And so that's a parallel fan out. In terms of a circuit diagram, let me draw what that looks like. All right, we can draw that like this. Here's our battery. Here's our generator voltage. Here's a switch that I've sometimes been ignoring to draw. Here's one transmission line. All right, we're going to divide this up into two transmission lines. I'm going to draw one going off this way. The actual direction that I draw it doesn't matter. What's important is that there are two transmission lines, and they're connected in parallel. So here's the next one here. All right, this would be, let's say this transmission line has value Z1. This has value Z0, Z1, and we've got Z2. Make this bottom one too. Okay, to connect this in parallel, we're going to connect all of the upper conductors to each other. So these three will all be connected together. And we're also going to connect the bottom three to each other. So this bottom connector will be connected to that one, and this bottom one will connect over here to that one. I think I can do better than that. In terms of drawing. All right, and that connects like that. So this is parallel fan out because the top three, or the outer conductor, if you prefer, are connected, and the bottom three, or the inner conductors in a coaxial cable, are connected. Okay, in this case, we're going to go through the same thought process that there's going to be reflections any such way that a wave approaches. And so, for example, we're going to have a reflection coefficient right here. And we're going to call this in black, actually. No, I will do this in red. We have a reflection coefficient here. We'll call this gamma 0, comma 1, 2. Right, this is the reflection coefficient for a wave coming along gamma and approaching the junction with 1, 2. We can define that everywhere. We can have a reflection coefficient that is coming along Z1 and hits the 0, 2 junction. So this would be gamma 1, comma 0, 2. And finally, this reflection coefficient is gamma 2, comma 0, 1. All right, so what are these reflection coefficients and how do we define them? So let's think about this from the perspective of a wave that's coming in that way. The moment the switch is closed at t equals 0, we have some input voltage that's launched into this wave, into this transmission line. And it hits this junction where it sees both Z1 and Z2. What would you expect the reflection coefficient gamma 0, 1, 2 to be? So let's write that down. Gamma 0, comma 1, 2 will be equal to, I'm going to put a placeholder there for load resistance minus Z0 divided by something to represent the loading plus Z0. Right, the question is, what are we going to put here where this question mark is? So since these fan out lines are connected in parallel, the load is basically the parallel combination of Z1 and Z2. So I'm going to write in Z1 parallel Z2 because that's effectively like the load resistance that the wave sees when it reaches that junction. Just to remind you, when you take the parallel combination of any two resistances or impedances, it's the product divided by the sum. So Z1 parallel Z2 will be multiply them together, Z1, Z2, divided by add them together, Z1 plus Z2. The parallel combination of any two resistances is always less than the value of either one. So if Z1 and Z2 is 100 ohms and 50 ohms, then the parallel combination is going to be less than both 100 and less than 50 at the same time. Right? It has to give you something smaller. All right, so Z1 parallel Z2 is less than Z1, and Z1 parallel Z2 has to be less than Z2. Right? Those are rules you can always remember. It's a good sanity check if you ever are taking a parallel combination, right? But remember this. And so it basically, everything is exactly the same as far as the reflection coefficient goes. We just have to treat the load as two parallel impedances, and we just have to combine them together, okay? So that's the reflection coefficient, but we've still got a separate problem, which is what voltage is now launched into these two transmission lines, Z1 and Z2. So because of the fact that these are now connected in parallel, we are forcing the voltage on Z1 and Z2 to be the same at this junction. And because of that, we're going to have tau 0, 1, 2 will be equal to 1 plus gamma 0, 1, 2, which is to say that the same voltage will be launched into each of these. All right, and that value of that voltage will be Vn times tau 0, 1, 2. We're going to get the same voltage value launched into both. That's a consequence of the fact that these two fan-out lines are connected in parallel. And so they are forced to have the same voltage, and so they both must accept the same voltage wave injected into them. Okay. Once you keep this rule in mind, you can trace everything out the same way as you did before. But just to make it clear, let's also look at what gamma 1, 02 is, just to make sure that we can define that correctly. Gamma 1, 02 is the reflection coefficient for a wave that is coming backwards on Z1 and arrives at this junction. And when it arrives at this junction, it's going to see a parallel combination of Z0 and Z2. So we're going to write Z0 parallel Z2. That's our substitute for our load impedance minus the line that's carrying it there, divided by the sum of those two. All right, and you can repeat the same thing for gamma 2, 01. And same for the transmission coefficients as well. Okay. So that's called a parallel fan-out. And the important part here is that the same voltage is injected into these two transmission lines after that first wave strikes the boundary. However, because these lines are in parallel, the current on these two transmission lines are quite possibly different. If Z1 and Z2 are different, the currents on them will be different because this tau 01 times Vn represents the voltage that's injected into line Z1. But the current that's injected in is that voltage divided by Z1. The same thing for the voltage that's injected into line 2. Take that voltage and divide it by Z2, and that's going to be the current that's injected into these. And that kind of makes sense because if I have two resistors connected in series, I can guarantee you that their voltages are the same, but their currents are different. Assuming that the two values here, R1 and R2, if R1 and R2 are different, we're going to have different currents in between them, or flowing through R1 and R2 separately. So a parallel fan out guarantees the same voltage is going to appear on both lines, but it does not guarantee that it will be the same current. Okay, with that, we can now talk about the third possibility, which is series fan out, and we're going to get to that in the next video and complete this lecture on series and parallel fan outs and cascaded lines.